Good morning, everyone. Welcome to our event today. I'm Cynthia Rogers. I'm an advisor with Barnes Global Advisors. We are the host of the platform today, and I'd like to welcome all of you to the event. I am your go-to person if you're having any technical difficulties or challenges with this platform. It's a unique platform that we introduced about a year ago to our customers, and it's been going over very well. So just quick housekeeping information. We will be doing a presentation up until noon today, and then at 12 o'clock we will go back to the tables that you were just sitting at, and you can engage in further conversation with our presenters today. As well as if you'd like to leave a message or chat, there is a chat box option to your right, and there is also a Q&A option. If you have questions for any of our presenters during the presentation, please leave them in the Q&A box. And we have an opportunity there as well to upvote the questions so that the top questions will get answered. And anything we do not get to, you can engage in the table conversation after to follow up. So without further ado, I'd like to hand it on over to Brandon Lamoncha, the Director of Additive Manufacturing with Humtown. And take it away, Brandon.
All right, thanks everyone for joining us this morning, or early morning for any of you that are on the West Coast, or maybe even afternoon. I think we had some people sign up from Europe. So, just glad that everybody's not too burnt out on webinars, and we're all anxious to get back out and do things in person and see people. I went to AMUG in Orlando. Was a good event, had about 50% of the people for the Additive Manufacturing Users Group. But, really just wanted to do, this one last online presentation to kind of, for the people that aren't able to travel and the countries that we're not able to visit, in this unique platform, Remo, it's a little different, but I think it gives a little bit of interaction, before the conference, and then we'll do some Q&A in here, and then we'll go back out to the tables, and I really suggest that you stop by nTopology and talk to Ryan and some of their team members, or go and talk to Philip and Ryan Stebbins from Penn State University on the work that they're doing. So don't be shy. Hop in, turn your camera, turn your mic on, and say hello to them. But I'm Brandon Lamoncha from Humtown Products. For those of you that don't know me, we are a primarily supplier to the metal casting industry. We started in 1959 as a pattern and tooling shop. Started making sand cores and molds as a commodity, basically, to the regional foundry industry in the 70s. In the early 90s, I started running 3D CNC machines and ran our CNC department for about 15 years before additive really came on our horizon. We started using FDM for pattern tools, but then now we're primarily almost all invested in additive manufacturing using binder jetting for sand cores and molds. So that's really what we're going to talk about today, is using some of these newer steps of additive manufacturing. And I'm going to share my screen once it's up. But not only additive manufacturing, but the tools that we are used. Give me 1 second. Get into presentation mode. All right, there we go. But really, designing the future, for sand printing, and using the tools and some of the partners that we had to work on this amazing project. We're very honored to work, with Dr. Ryan O'Hara, Ryan Stebbins, and Phil at Penn State. This is a really fun project. I don't get to always report out and show some of the projects that we get to work on. Using additive manufacturing, we're kind of in next space technology, so it's not always where we get the opportunity to share that. So I was really happy to work with this team on this project where we were able to report out, what we were able to do using these technologies. So as I mentioned, any of you that don't know Humtown Products, we have 2 facilities, the 3rd generation pattern shop and core shop in Columbiana, but now we have 100,000 square feet of dedicated space for additive manufacturing. Recently, we were the 2020 Manufacturer of the Year. And the reason I bring that up is because in the National Association of Manufacturers, they said, making the judgment of who was going to win, they basically said that it was Humtown's utilization and commercialization of 3D sand printing that really made the deciding factor. So, it really goes to show that additive manufacturing is being adopted not only here in the United States, but worldwide. We're shipping product, not only in, Canada, Mexico, Brazil, but we've air freighted as far as Indonesia. So we're starting to see this as a global trend. But like I said, that's not, 3D sand printing isn't really even the focus of this talk today. Today, we're talking about advanced manufacturing as a whole and the partners that we partnered up with to use to design, a really exotic part that would not typically be thought of using sand casting, and the tools to ensure first-time success. So, we'll talk with nTopology with Ryan O'Hara on the design, and then design for additive manufacturing with Penn State. We're going to touch lightly on the simulation. We used a partner at Flow Science for simulation. We'll talk a little bit about the mold being printed at Humtown. And lastly, it was poured at our partner, Trumbull Foundry and Alloy, locally. So without further ado, I'm going to kick this off. I'm going to let Dr. Ryan O'Hara turn his mic off so that he can give a little brief introduction. And I really want to focus on the technologies that we used to achieve this process. So go ahead, Ryan.
Yeah. Hey, thanks, Brandon. And just wanted to say thanks for everybody for joining. And then I'm super excited to interact with folks afterwards. So unfortunately, can't be in person with you today, but maybe we can make some connections after the fact. And then maybe we'll save beers for the next time we meet. So with that said, I'm Ryan O'Hara. I work for a company called nTopology, and we're kind of like a next generation design software for manufacturing, and specifically advanced manufacturing. Oftentimes, though, we're able to make really complex shapes, and we get tied directly to additive manufacturing, when in fact, really additive or manufacturing in general is a multi-process step to produce a part, right? And we're all aware of that. And so I joined prior to nTopology. I was in the Air Force for 20 years, working a lot of R&D and like pretty technical things for the Air Force. Was using the nTopology tool when I was retiring, and made a lot of sense to go forward. And I really see our software kind of being the future of computer-aided design in the future. So, go to the next slide. Okay, and then actually, if we could get the text up there, right? Yeah. So what is nTopology, right? And we're really just a computational modeling platform for design, simulation, and when you couple those together, you're able to do advanced manufacturing. And the way we handle geometry is we actually use implicit geometry, and that implicit geometry is for it allows us to generate shapes volumetrically, and we're able to do that really quickly. With that said, we also take a field-driven approach, and so we use fields in every day when we do design. Oftentimes it's a flow field, or maybe a stress field, or displacement field, and typically the designer will use those fields to influence their design, either to add or remove material. And we can actually do this programmatically in our software. And then finally, once you're able to generate a design, we actually allow you to store and keep that workflow so that you can reuse it down the line. And so, yeah. We'll go to the next one. Okay. So with that said, I was reaching out to partners to work on a collaborative project, and one of those things that we've done here is that you'll have to forgive me, my children who may have forgotten that we're doing a webinar here, so we may hear some noise in the background. With that said, though, we've had one of the big things is that in manufacturing, you might have common platforms like a robotic arm, right? Especially when we talk about efficiencies in the workplace, and and making things repeatable in that sense as well, and bringing automation in. So one of those things that we wanted to do, though, is, for an example, is use a robot arm in this case, where this part is produced via casting, right? And we thought, hey, using our software via nTopology, could we actually use a topology optimization method to actually lightweight that part even further, right? And for us at nTopology, this was a big deal because this robot arm was over 1 meter in length and about 400 millimeters in diameter. And so although additive manufacturing is great, it's not really the best way to produce large geometry. And we need to go to more traditional processes like sand casting. And that's kind of where Humtown and Penn State came in. So this is the motivation here, is to produce this optimized part with a 58% mass reduction. Okay. We'll go to the next slide here. Yeah, so with that said, you know, in terms of advanced manufacturing, again, going back to this multi-step process of producing an optimal part, right? So casting, so design and simulation is one piece of this, and then the casting and then the final machining are the other parts to this. And so, you know, we needed to partner with, in this case, Humtown and Penn State, and we also included Flow Science in this to do some casting predictions to help produce an optimal part. Especially when you consider about the size of this part. I think when we initially planned this, the size, you know, added a fair bit of cost in terms of the mold. And so we need to make sure we got this right the first time. And so that's where we brought in Penn State and Flow to help out with the core and mold design. So, and as you can see here in the image, this is kind of the multi-piece part that is able to produce a lot of complexity in here. And I think we'll be talking about some of the other features in terms of like advancements in casting and mold design. Okay. Good. There we go. Yeah, and so again, you know, you ask, you know, in terms of topology optimization, what does that really mean? And the key here is that we use a common method. It's called the solid isotropic material with pixelation method. No one ever really says that. They just say, oh, it's top-op, or I use top-op with SIMP. Right, and the idea is that this SIMP method gives you a material distribution and based on density, and then we use that density to basically just put material where it needs to go. And then oftentimes we just call this a load path visualization. Oftentimes engineers will do this by applying loads and looking at the stress and looking at the colors in areas of high stress and areas of low stress and removing material. In areas of low stress. And we're basically doing that in this scenario, and we're optimizing this part for stiffness while minimizing weight. So that's the key here. So we have a really stiff part and with minimal mass. We can go to the next slide. And so in terms of what that looks like, it's ideally you would have a large design space, right? And then that design space is going to produce this density field, right? And so we think of load path visualization, where we use that density field, and then we basically, you'll notice it has like a jagged or rough edges, and that's part of the process where we use the simulation tool, or FEA, to volumetrically digitize that shape, and then we basically remove elements as we need based on the density field. So we have some tools using our implicit modeling technology to smooth that, and then we're basically able to add in those critical interfaces. And then ultimately, we can actually bring that back into a CAD environment with these NURBS patches. So that's kind of how you're getting your biologically inspired shape, is just optimizing for this material stiffness, and you can kind of see the different parts in the process. Okay. And then in terms of load path visualization, so when we talk about that density field, all I'm doing is in this video is we're changing the density threshold. So that's the little box in the lower right. And as we change that density threshold, we're seeing where the material is needed or not needed. And you can, in our tool, we basically allow the designer to pick a target threshold, but we do give them the option to kind of pick, hey, maybe I need just a little bit more, or maybe I want a little bit less than the original goal. And we're basically able to visualize that. But oftentimes designers too will just use nTopology just to do this load path visualization, and then maybe even use their own CAD tool to like identify areas where they don't need material. So, okay. I think that, okay. Yeah, and at the end of the day, right, we basically just get a final part that's ready for machining or manufacturing. But, you know, as we all know, on the design side, there's the final design, and then there's the design for manufacturing, right? And so at this point, you know, I had to reach out to Brandon, who then reached out to his contacts at Penn State and also at Flow 3D to bring in partners to kind of help us, right, with the final design that was going to be used for the casting piece, right? So we had the final design of the part, so it would work on the machine, but now we needed to take that next step, and I think that's where, if I plan this right, yeah, we can introduce the folks on this. I do want to highlight, though, you know, nTopology was just responsible for the design, And then Philip and Ryan over at Penn State kind of took over this design for manufacturing. Then we worked very, very closely with our flow science friends over at Flow 3, who are not on this call, but that was a big piece of this, and I believe Philip's going to talk to that. So, yeah, thanks again. Look forward to talking with you folks.
Hi, so brief background about me. I did my undergrad at Penn State in mechanical engineering. I'm currently in my second year of my master's program in mechanical engineering, again at Penn State, with intentions of receiving a minor in additive manufacturing. I'm part of Dr. Manahoran's The Shape Lab at Penn State, and my research is primarily focused on redesigning runner extensions to reduce casting defects, utilizing 3D sand printed molds for more novel designs. Next slide, please. So I'm sure many of you are already aware of sand casting, but I'll just briefly go over it. And you got your sprue, runner extension, and riser. All of these are vital for ensuring a quality casting, reducing defects. If you have a great design like nTopology came up with, you need to have the proper gating and rising to make sure you get a quality end result. That way you're not getting high scrap rates and low yields. But some of the limitations with traditional sand casting is you're not able to get some more unique designs or geometries for these rigging components. Next slide, please. So this is just a quick image of what Phil will go into greater depths on of the rigging design that was come up with for this robotic arm. I'll kind of touch on the sprue a little bit and just 3D sand printing in general. Next slide, please. So the main benefit, I guess, for 3D sand printing, like I've touched on already, is the ability to create some novel geometries for rigging and kind of overcome some issues or challenges with traditional rigging, like high turbulence or in-gate velocity that may cause porosity defects or oxide formation, the placement of risers and even the geometry of risers in order to prevent solidification defects like voids or pinholes and stuff like that. So that's the main benefit of 3D sand printing from a rigging perspective, is you're able to tailor your rigging geometries for the design more easily and with optimization. Next slide, please. So a quick example of where you might see this is with sprue designs. Sprues are pretty important when dealing with filling related defects. It's major in reducing or causing turbulence in the melt and increasing velocity, which, like I already said, could cause filling related defects and porosity and oxide formation. So this is one area that you can, and we did for the robotic arm, focus on redesigning and utilizing 3D sand printing. Next slide, please. So this is some results from previous research done by a member or former grad student in the Shape Lab. You can see you got a traditional straight sprue, a parabolic sprue, and then a conical helix sprue. The goal was to see, or to prove essentially how 3D sand printing and redesigning the sprue can impact in a positive manner casting quality. And you can see from the CT scans the reduction in porosity or entrained air with the conical helix versus the other two. And this conical helix is pretty complicated and is not really possible or feasible using traditional methods. So this could be scaled up or modified for all sorts of geometries and sizes of castings, as Phil will go into a little bit more. Next slide, please.
Hello, I'm Philip King. I'm a PhD student, also in the Shape Lab under Dr. Manoharan. My research focus is primarily in novel rigging geometry, so these conical helix and parabolic sprues that are only able to be manufactured via 3D sand printing. And then also another aspect of my research is in embedding molds into sand, or embedding sensors into sand molds using 3D sand printing, so we can actually print a mold with a little cavity and place a sensor in there, and then able to get data during filling and solidification that otherwise would be unavailable to us. So next slide, please. So as Ryan alluded to, he primarily talked about, I guess gave an overview of the different things we can use 3D sand printing for to optimize our system. So the idea behind this was we were already going to need to print out the robotic arm casting. And so if we were already going to do that, why wouldn't we print a novel rigging geometry for it so we could get the highest quality casting possible, rather than just throw on your standard straight sprue, straight runner, and just cylindrical risers. So with that in mind, we took this casting and then started designing a conical helix sprue as well as novel spherical risers so that we could get the highest quality casting possible. Next slide, please. And so here again is the picture of the final product that we came up with, which has a conical helix sprue on one side and then this long runner. With our goal was to fill the casting evenly, and I'll go into in the next couple slides about how when we were working with Flow 3D, looking at the simulations, iterating through that, we'd see that we get uneven filling depending on where the sprue was, and eventually we figured out that the best way to evenly fill it is to have a slightly tapered runner and then have two gates on either end of the casting so it would fill slowly. Next slide, please. So now I'm going to talk more about the simulation. So basically, the way we started with our workflow for the simulation with working with Flow 3D is we started out with a solidification model and figured out where the hot spots were and where we would need to place risers. Then next, we tried this design where we were trying to minimize the amount of area we needed for this mold. So we put a conical helix sprue right next to the casting and then just put one riser on top to see what would happen. And when we did this, we were still getting areas where we didn't fully fill the casting, and also we would get hot spots during solidification. So once we saw this, we then started messing around with using these spherical risers that we could only really place using 3D sand printing, and also moving our sprue location so that we would get even filling throughout the whole casting. And so finally, when we got to the on the right here, this design, it's where we placed numerous risers in our problem areas. And then also we had the sprue on the one end with that long runner so that we could facilitate even filling throughout the entire filling process. And so next slide, please. And so here, if you play the video. So here is just the final model we had of filling with Flow 3D, where you see we have very slow filling that it, so we don't get splashing occurring during filling. And this is due to the conical helix sprue slowing down that melt, and also the long runner taking a while to fill up so we don't get turbulent filling, which will reduce our defects in this casting, which is especially important for, you know, the topology optimized casting where you don't have these large, we don't have that high a margin for error with these small surfaces. So next slide, please. So yeah.
All right, can you hear me? All right, hopefully you can hear me now. Sorry, they had to mute mine for a little bit of feedback. All right, so yeah, thanks guys. That was great work. At that point, basically, I'd been involved through the whole process, but obviously there was a lot of design and iterations going on back and forth. So now, basically, after working with the team at Penn State and nTop, we developed a design that was going to be printable and a gating system that was going to be unique. So basically, at this point, the team at Penn State threw over some files to us at Humtown. We were able to throw that into our large format 3D sand printers. And as you'll see here in a moment, the mold was extremely large and done in multiple pieces. But this is our current manufacturing facility. We currently have 7 S-Max machines in this building. So we're growing, very, very rapidly because of the adoption of this technology. And, we may not see every mold and core 3D printed, in production, but there's definitely a lot of applications, in smaller consolidated cores where we are seeing, this. And, if this design were to go to production, there's hybrid methodologies, where a pattern could be constructed and then the internal core, that is very complex could be printed even into production. So for those of you that are not familiar with the 3D binder jetting process for sand molds, the sand is the aggregate that we use for making the mold. It's vacuumed up into a hopper where it's mixed with one part of the additive, and then the print head, as you see now, deposits the binder. It's a 2-part system. That cure takes place, we can print, and then we basically harvest the parts out. So anything that is white sand would just be reclaimed sand that could be used again in the printing process. And what you see, the green part is the fully reactive core. We clean those cores after they're harvested, we package those up, and we ship those out to customers, as I mentioned, all throughout the United States and Canada, Mexico, etc. So that's the 3D printing process. As I mentioned, we're not going to focus a lot of time on that today, just as we're not going to spend a lot of time on the casting. The real effort and the real meat and potatoes of this project, was done, in the very early on design, in the designing for additive manufacturing, and then the simulation and those iterations that went back and forth. This was the sand mold. We're gathering more pictures. I believe we have a video, maybe on nTopology's site and maybe on ours. We'll get all that. But this was the mold after it was printed. The mold was harvested, packaged, and was taken to Trumbull Foundry up in Niles, Ohio. They do automotive, castings for, aluminum. So they have an aluminum foundry. One thing to note was how large, this package got with the gating. In the novel design, our yield obviously wasn't very good, but, we were able luckily, we were able to pour this all in one shot at the foundry because they had 1,000-pound melting capacity, and we used just about all of it. So it was, even though you have all this technology and everything, we got to the foundry and they're like, our ladle's only 800 pounds, so we did a direct pour right from the furnace. So it was a great project, had a lot of fun. As you can see, we bolted the mold together. We ended up putting some straps around it just to keep everything tight. But here we are, we're doing a direct pour right out of the furnace into the mold, and there's more to come. We have the casting now. We're going to do some finishing on it, minor grinding, and we'll have some photos of that here shortly. That's a beautiful thing. All right. So that was the project, talking about the designing, and for the future of sandcasting. I think the big takeaway that I had, when Ryan, called me up from nTopology, the first thing I thought of was, well, that's usually used in direct metal printed parts. I don't usually think of that, for 3D sand printing and for sandcasting. So I think, the big takeaway, from this project for me, and I'm sure many of the foundries that are on the line watching, is, there is software packages out there that we can, develop, and we can use, better design tools, to get to, to higher quality of castings. So with out of the presentation.
Brandon, we have a few questions that
Yep,
we can go over.
that's what we're gonna hop onto now. So Ryan, if you saw one that strikes your eye, when I was in full presentation mode, I wasn't able to see the questions. So
yeah, no problem.
But yeah, go ahead, and if you saw one you want to tackle, I'm going to just peruse through them now.
Yeah, so I think overall, I just wanted to highlight, I learned a ton in this. I don't know, I don't have all the backgrounds on everybody who's attending, but I imagine it's a lot of foundry folks, right? And I just want to apologize to all the foundry folks ahead of time and say, oh, I didn't think of, prior to this project, of foundry really being advanced manufacturing, right? And maybe that's just and just because I've been an aerospace person and a lot of subtractive manufacturing, but really, as I learned, I was really impressed by the tools, and then the knowledge base of Brandon and the foundry and the Flow 3D folks, and all the effort that goes into making it making castings as common as they are in our everyday lives, right? And I think I maybe took that for granted. And so, and I think too, so I certainly lump sandcasting into advanced manufacturing now, for sure. And the other piece to that was that, in terms of production, right, I think one of the other biggest things I learned is just how many parts are produced via casting, right? And then, and that's a key capability for us both nationally and more broadly in the global economy. So I think there were a couple of things specific to nTopology that we talked about. In this case, it was for what load case did you optimize the part? And in this scenario, we can optimize for multiple loading conditions. And in those scenarios, typically for a topology optimization, you would pick, if you had a dynamic load, you would pick the max dynamic load that you would use and use that in your design. And so we can include both of those. In this scenario, we included just basically what was given us to us for this part. And I think it had 15 different load conditions. And then in terms of, there was another question in terms of what nTopology designs for a specific process. So one of the things in our company name, the idea is that it's really any topology. So any design is what we want our designers to be able to achieve, right? And we do that by marrying these different technologies together. But the key is that we don't remove the designer, right? And you still have to design for that manufacturing process. And I think in this scenario, actually, in this scenario, we could have used nTop to design the runner and the gate and all the risers. But in this scenario, we actually just leveraged Philip and Ryan at Penn State using SolidWorks, right? And we use their design intent to actually produce the part for manufacturing, right? In that scenario. And, Philip, I'm trying to remember, I don't think we had to change much in the design ahead of time from the casting standpoint. There weren't any big conflicts with the mold as far as I can
No, the only thing we did was, I think, in the hubs made those solid, and then we're going to cut them out later.
Yeah, and we did a few things where we tried to optimize for flow, right? What change if so and then there's a few others here. I do want to, Mark Osborne made a comment about that he saw a lot of turbulence in the runner, and I just want to caveat that, I was working on a project really, and it said at one point, you have to shoot the engineer, right? And so we ran about 5 different iterations, and then we said, okay, we really need to make this thing. And so we're going to go with our best, but even a designer, and Mark, maybe you would even agree, we probably could have done a little bit more, right, to get to a truly optimal design. And I think we always can, right? But at some point, you just have to make a decision that this is likely to be the best. And so, yeah, I think the key here is just to highlight a lot of the technologies, and that really you can do anything you want and kind of optimize for those things, and all the tools are in place to do that. And I think I guess a big key is, right, having the right people. And I think in this case, it was really a lot of fun to work with Humtown and Penn State and Flow to kind of achieve that optimal design.
Thanks, Ryan. So, Phil, to those points, first of all, did you have anything to speak to on the wave reflecting back? I mean, was it just, we had put some, not unrealistic, but we put some pretty tight timelines on you guys. We were working weekends and we were trying to get this out. But, was there something that, that you would like to speak to that? Any further any detail than what Ryan had mentioned? And I agree. I mean, sometimes you just have to say, stop, let's just go. But, from your iterations with Ajit at Flow, what are your thoughts on that?
Yeah, I think most of it was we just ran out of time. I thought, I know Ryan Stebbins here, we were talking about maybe trying to do different novel runner extension designs too, but at the end of the day, we just ran out of time and ended up just leaving it as was because that was the best iteration we had.
Yep. No, and that's completely understandable. And I think, I know Mark, and, I think, there's many times where we would like to take, design and, simulation further, but, at the end of the day, we got a customer screaming, hey, we need to get this out the door. And we did. We had a nice even flow. The casting did turn out good. So I think, yes, if we were going to go into production, but we overgated this. I feel, there was, I would definitely want to improve the yield and try to get that runner, the diameter of that down. I mean, it added, I forget it, quite a bit of weight to the overall, from the casting with the original rigging, to the pour weight. Like I said, we almost had to get a bigger foundry, to pour it. So definitely some lessons learned, and we didn't circumvent all of the these tools. You still have to have the people involved, and you still have to have the engineer, and you still have to have the designer. And I think you guys did a great job. Maybe for Ryan and Phil, what would you change if to do a different metal like iron? Obviously, this program was only focused on the lightweighting of a robotic arm, which probably would never be made out of iron. But process steps, pretty much everything would be pretty similar. To running the simulations, and you'd obviously use a different gating calculator. But any major, I don't see any hiccups or any hurdles, switching alloys. Do you?
Yeah, it's pretty much the same. With the sprue design, it does change a little bit because when you calculate that, it has to do with the material properties some, but other than that, it's probably just going to be pretty similar.
Okay, that makes sense. Kyle had a question. What would the benefits be to use a conical helix sprue versus a traditional straight sprue? And I think he lightly, maybe Ryan touched on that. I don't know, Ryan, if you want to go in more depth, or Phil, if you want to field that question.
Yeah, Ryan, you can.
Yeah, I was just going to say the main thing is just reducing turbulence and in-gate velocity. The conical helix, I guess, allows some angular velocity. So kind of instead of getting, you want to reduce the velocity below 0.5 meters per second. So conical helix allows you to do that. Whereas the straight sprue, you're kind of just having a free fall drop from the basin, which induces turbulence and can cause high velocities. So it just really kind of reduces filling related defects like entrained air, porosity, for aluminum specifically, oxide formations and biofilms and stuff like that can get into the final casting and cause reduced mechanical properties.
Yep. No, very good. I think we touched lightly on that, but and then obviously all these people are welcome to come to the Penn State tables and take some of the gating questions in more depth. I know you guys have done a lot of research, and we are still developing. A lot of this is new, and a lot of people look at that and say, why would you do that? But, there are reasons. I mean, you've done the math, you've done the, so I encourage people to say, we're still developing some of these, these opportunities for these novel gating concepts. And we're not saying that they're perfect, but we're just saying, this is, opportunities that are, now that we're 3D printing molds and cores that we can incorporate. So very good. One other question I had here, and I think I can field this one. Michael had asked, do the 3D printed pieces have similar hardness to a cold box core? Yes, we can definitely achieve, very similar hardness. What we do find is that a cold box core has a smoother surface finish because you're actually blowing that sand into a die under pressure. So you get the resin wipe, that pushes out to that surface. So when you feel that cold box core like we make in our Columbiana facility, they are very smooth because they're basically a product of the mold. Here, we're just laying sand grains on top of sand grains with, light, recoater that has some, some tamping action, but it's definitely not as dense. So, but strength, we've made cores as high as, I don't know, I think 600 PSI on a 1x1 tensile, bend, 3-point bend test. So, we produce cores in our 3D printing facility, as hard or harder because of uniform density. We do get some spongy cores, especially in water jackets and, very thin lacy cores, out of the die. So, we do have a very similar hardness. So I think we've fielded most of the questions, which I appreciate everybody, writing into the Q&A.
We got one more.
Oh, I do see that. It came in through the normal chat. Go ahead, Brian. I didn't read it yet.
Yeah, no, it's fine. So Richard Lopez asks, is the future for a project like this an integral marriage of model generation, stress analysis, and castability optimization? Seems like ideal optimization can't be realized until, I think until all the tools evolve, and it got cut off for me over here. So, I think Richard, to your point, I talk about this all the time in our software because in nTopology we do have an optimization tool, but it's a very structural optimization for a very particular set of boundary conditions, right? In this case, maximizing for stiffness, right? Well, what about heat transfer, or what about multiple loads? And then at that point, I know we talked about automation and easy buttons, but you still need smart people designing your products, right? You need design engineers, you need manufacturing engineers. And I think the level of complexity that you can do is still very high. And then the time frame that you can do it in is also very, I think, Brandon, we spent we kind of stretched things out and did this maybe in 2 months or so. So, I mean, and I think we could have done that faster, right?
Oh,
and if we did another one again, a lot of it was just a lot of get to know you sessions and who should we bring in. But once we had that team assembled, it went really fast. And so I think
from your final design to being at the foundry board, I think correct me if I'm wrong, guys, but I thought we were less than 2 weeks. It was very quick once we had everybody on board. And, like I said, people were, once we pressed go, it was less than 2 weeks and we had a casting. So,
well, and then Brandon, to your team in Trumbull, from when we had the design finished from Phillip or the Penn State folks, I think you were you cast it on a Monday, or no, you printed the mold, finished the mold on Monday, and then we're casting it on Wednesday. And I was blown away how fast that was, right? And so, that rapid manufacturing capability is there. And I think maybe to answer Richard's point is that I think there is no magic button to connect all the dots, but it's also based on your process and what you're trying to design, and you're just going to see all those timescales shrink, and you're going to be able to do it with much higher confidence, right? Having the CFD simulations and all these things in confidence in a final part. Yeah.
The last part of his question said, will software of the future be able to incorporate solidification as well? And I think maybe what he means is, could you design, work through the design for manufacturability and then also simulate all in one package? You know what I mean? I would, from what my understanding is, I think software, if it was written, it could go through those steps all in one package. But, there's also merit to having different independent softwares, and then just, bringing them, together. But I mean, I don't know, Ryan, that's probably more for you. Do you see your software being capable of, partnering and incorporating, with other softwares so that you basically put in your need at one end and outputs, a mold package that's been simulated, ready to go? I mean, is that possible?
Like, we're also a young company, right? So we've only been around for, I think, a total of 5 years, with 2 years of our product being available. So we're looking at the viability of all those things, and if it makes business sense, I guess we would certainly consider it. At this time, our intent is to be as flexible and be able to integrate with as many processes as we can. So simulation is a big part of that, et cetera. I think Mike Browning also had a good casting question.
I did. I just read that. So basically, yes, if we had time, we would have probably, printed, we could even have made a pattern, and this could have been done as a hybrid project. I mean, the outside of the casting, wasn't terribly complex. Most of the complexity lied in, so we could have, even built a pattern if we needed to make 10 or 100 or 1,000 of these. But, to his point, to keep the cost of the print and mold down, we definitely could have, kept that shape smaller, and then incorporate, and then, use like air set, at the foundry, to back that up. So the answer to that question is definitely yes.
Yeah, and I think the key, right, for a lot of these projects, and the role I have in nTopology, is just to show what's possible and then bring partners together, just like you would at any business unit, partners together with different capabilities, and demonstrate how things can be done, right? And I think that was the big goal of this, versus a perfect one. And I think we learned a lot. And hopefully through this webinar and in other presentations, we're also sharing that with the community, right? So
Yeah, no, we haven't done any X-ray or any, follow on to the casting. It was like Ryan just mentioned, it was more, to show the art of the possible, the tools. And, I mean, if we had time and unlimited budget, and, we would definitely want to, go back and, do, an X-ray of this. You got to remember, this casting is a meter long. I don't know if there's an X-ray machine out there that could, we could X-ray the whole thing. We could, but yes, I mean, the casting had a good fill. It was, but there was, so anyhow, I don't think that was the scope of the project. And, it was really more about the design tools and, the process inputs. But yes, there's a ton of validity to go back and actually make sure, that all the simulations and everything, came to fruition, that they all were represented in the casting. But, Magma and Flow, and, they've done, hundreds of thousands of dollars worth of research, and they have their own projects on that. This was more to demonstrate, what tools are available. And as I mentioned, most people that I talk to in the metal casting and sand casting, are not familiar or have used topology optimization for sand castings. And I'm sure there's some out there that do and that are very familiar, but I would just say, from the broader sense, people think of that technology being used for direct metal printed parts. Whereas we wanted to do this presentation to show people that, with 3D sand printing now more than ever, we have new design tools, new methodologies for designing for manufacturability. And, we wanted to bring those to the table. And like I said, I appreciate all of you guys and your time, to, as in this project, and to come do this webinar with me, just so that we can get that out to more and more people in the metal casting world.
This was really fascinating. A great presentation. Thank you all for joining this webinar. Thank you, Brandon, for hosting and pulling it all together. Just a little bit of housekeeping as we go over. We'll be going back to the tables. If you'd like to engage with any of our speakers today, just simply double click on the table that they'll be seated at. The names of each of the companies is listed at the table, and you can have some follow-up conversations, and the floor will be open here until about 12:30. So thank you again. I'm going to send us back over to the floor.
And Cynthia, one thing I wanted to add, like, for all those on the call, if you have a cool project and you want to do something, and you want to, like, share the knowledge with the community as we go through a process like this, I think both Brandon and I are interested in those opportunities. Yeah, so please reach out or stay on for the follow-on.
Yeah, and also, to just reiterating, the recording of this will be available. I believe that we'll be putting it up on the Humtown YouTube channel, so you can review it again. And if you have any additional questions, reach out to our speakers. All right.
Thanks, everyone.
Thank you.